Defining possible seems to be the theme of tonight, but I'm going to be talking about connections, how we make connections, how amazing the results can be. Well, it might not seem, relevant, but we'll get back to that. Now, every now and then we're told, we read in the news or in books or so, that certain geniuses, they came up with these results, profound results. And why? Because it's creative thinking. They think creatively, and it's a key skill to have if you're a genius, apparently. And I think to be able to make connections, of whatever sort, it can help you think creatively. Greatest puzzle solvers of all time, Holmes and Watson, they, deduction, making logical connections step by step to come to a solution. Who wouldn't want to think like them? But I'll be talking about how certain connections in science, particularly, have changed the way things were before. So different types of connections there are. Unification, where basically you have two different ideas, and you make a connection, you make a link, whereby the link is so strong, so fundamentally strong and true, that you say basically they're the same thing, and you merge them together, unify the two ideas. Another is deduction, just following step by step through logical arguments and reaching a solution or a valid conclusion. Another is borrowing ideas from different areas. Now, say if you've got a particular field you're working in, and you've got a problem in that area, and say there's another area of study, say, and there was a similar problem there, and they'd solve that problem, and what you do is you take that solution, reform and adapt it to solve your problem you have originally. Well, basically what it means is to bridge two different areas to, extend your ways of thinking, looking at things. In the mid-1800s, someone did an experiment. Oh, seems to be a connection forming. Well, let's see. So we've talked about different types of connections. Okay, well, let's just start. We'll see how it goes. Different types of connection, good. So in the 1800s experiment, setup was, there's a coil, and there was a magnet, and the coil was connected to a current sensor, basically. And basically the demonstration here, this is what it is. A coil here connected to a current sensor, and no batteries, no power source, nothing. All I have is this magnet here. Now, let's see, fingers crossed. Now, if I insert this magnet, just check the reading on the current sensor. And if I take it out, and again, and if I take it out faster, there's a bigger reading. So, you're inserting a magnet into a coil, and somehow, just by moving a magnet, you're getting a current in the coil. This is bizarre. It's like me telling you I've magnetized a ray of light. It makes no sense. And indeed, it didn't at the time. Well, the person who did discover this, Michael Faraday, and he proposed this idea that somehow magnets, a moving magnet, could somehow induce an electric current in a wire or a coil. Seemed crazy, but he was somehow unifying these two ideas using this idea, this connection here that he'd found. Indeed, what he'd stumbled upon was electromagnetism. Now it's known to be true, and basically all the power generation, electricity generation, is done through this. Electric motors run through this idea. Further development showed that light and color that we see are basically ripples in this field of this electromagnetic field permeating through space and time. And these ripples in this field are what we perceive as light. Quite amazing. Unifying ideas is profound results. Now, another physical theory that's often portrayed in the media as seemingly impossible to solve, and quantum mechanics. Brilliant theory, okay? But as with every brilliant theory, a great idea, this one too started with a light bulb. More specifically, this guy, this light bulb. Ping. He was asked by electrical companies to come up with more efficient light bulbs, how to get the maximum light energy out of a certain light bulb. And as any physicist would do, he studied the workings of a light bulb, or how much energy would come out, using the classical theories of the time. What he found was, this graph here. Now, the classical theory gave the black line, and what it basically means is that from a light bulb, an infinite amount of energy should come out. Now, surely that's ridiculous. How could you have infinite energy? Anyone could say that's wrong, but he found himself in a problem, and he had to rewrite all of current physics at the time. And what was thought at the time was that energy was continuous, like an ocean flowing fluid. You can't quantify certain amounts of energy. But he said, what if you can? He took that idea of quantifying, having packets of energy coming in packets rather than a continuous flow, and came up with his own theory, quantum mechanics. And his theory gave the graphs, the red, blue, and green lines, which were perfectly consistent with experiment. And just using this idea of making light bulbs better, essentially, he founded one of the most advanced theoretical physics theory we have at the moment. So it's pretty cool. Got another connection for me. So we've seen how different scientists, they've worked this idea of making connections, and they've made profound results that have shaped the world as it is today. Halfway there. Now, over the summer, I worked on a NUFU project, 4-week NUFU project, at a wind turbine company. And I too made a connection of my own, specifically between wind turbines, seeing that I was working in a wind turbine company, wind turbines which are big and ugly and make loads of noise and no one likes them, but are nonetheless an engineering masterpiece. And airplanes, which everyone tends to like because they take them to nice places on their holiday. More specifically, the flaps on the wings of an airplane. Now, with every such scenario, there's a problem. What the problem was, say you have the blade of the wind turbine. Well, let's just have this as the blade. And when wind blows on it, it has a force. It pushes the blade, like this red arrow here. Now, if the force is constant, it bends constantly, which is fine. Okay, if constant bending is all right. But if the wind speed changes, which it does, you get a really chaotic, turbulent amount of force, and you get a wobbling of the blade. And the wobbling can cause a great amount of stress on the turbine blade, and sometimes even cause it to break. And breaking it obviously reduces the potential lifetime of a wind turbine, which is a problem. So somehow we needed to fix this. And the key essential connection here was that, fortunately, the shape of a wind turbine blade and a airplane wing is the same. About the same technology is used. So the same way how an airplane flap moves to control the amount of lift produced, we can integrate somehow this technology onto the wind turbine blades to control the amount of bending produced. So we can reduce it to a constant amount. So plan of action. Design a flap. As with every engineering project, you do have to design something. Calculate an average bending, my value which I had to keep, I was aiming at. Then find the amount of greatest bending that would come. That was basically from databases. Then introduce the flaps, see would they be of any use by comparing it with how much it's been reduced. So, design. Well, this was a test I came up with. I had 4 different materials here where I compared the amount of load they'd be taking compared to the maximum load they could take. And there were 2 tests, and only one of them passed. So that was the one I was going with. And then there was the design. I mean, what type of flap do I want? So, well, this is a traditional one. Anyone who's been on a plane or seen a plane knows what a traditional one is. But they have gaps, which make noise. And seeing that wind turbines already make loads of noise, you don't want any more. Non-traditional ones, they're good because no gaps, they're more aerodynamic, and it's good. But as of today, there's no technology right now to turn the flaps. So, I mean, this is a model, small model, and they're turning the flap by hand. I mean, you can't have a massive hand on a wind turbine turning the flaps. Problem. So, I came up with this design. I designed it myself. This is a hybrid between both. It's traditional in nature, but I've added these neoprene rubber sheets here, and they're designed, shaped so that to retain the aerodynamics of the blade, and it covers the gaps, so no noise produced. Flap structure. Here's the material I used. Here's the foam, just to prevent the flap on wobbling onto itself and breaking, which is bad. Flap actuation, this is how it will be turned. Basically, this is a motor at the root of the wind turbine. And why the root? Because this just allows you to use the minimum number of rotors you could use, which is 3, which is really easy for repairs or replacements. I mean, there was a design where there were actuators all the way through the blade, which is just a nightmare in terms of engineering and everything. But what will happen is that the rotor would turn. It will come to this shaft. This shaft will be connecting 2 rods, because of safety features in case one of them breaks. It will be connected to the flaps. Flaps will be hinged on a bearing surface to reduce friction. And basically, as the rotor turns, there will be a wind sensor on the wind turbine sending real-time information of the wind speed, and the rotor will turn accordingly, and everything will be happening in real time to reduce the amount of bending. Materials used were cheap. Everything, as you want in an engineering project, everything cheap but durable. Now, for the calculation, the real bit of the research, one of the tables I did here, it's all right, you're not meant to see the numbers, but the main columns here are the green and blue ones where I've calculated the amount of bending that's being put on by the wind. And then after loads of Excel, loads of tables, loads of number crunching, programming, and loads of crashing, I finally arrived at this one table, probably the most important table of all of my research. And more importantly, the last 2 cells here, which say basically a turbulence reduction, or the amount of woblance reduction, of 54.85%. About 55, using just first calculations, an A-level student somehow reduced the amount of bending by 55%. Imagine what could happen if actual engineers worked on this further, put this further on. Now, I was pretty pleased with that. This is a realistic technology. It will be used in the next 5 to 10 years. And I suppose it would be nice to see one of them around and know that you've played a part. And you see how I and other scientists have used this idea of making links and connections, by first, identifying the problem in its crudest form, what it actually is. Looking for analogies in other areas, seeing how other areas, other similar problems have been solved. Taking that solution and then adapting it and reforming it to sort of cater for your problem. And it's just a case of solving your problem. But I think this idea can be extended to a more general sense. So next time you're stuck in a seemingly impossible problem, whether it be math or philosophy or whatever, why not try borrowing an idea? Why not try making a connection and seeing how it helps making you understand? And so this leads me to the very first two words I said, defining possible, the theme of tonight's event. I talked about how I made a connection in wind turbines and all, but I think the final piece of the puzzle, all of these ideas, all of these results that have come out of this making connections have resulted in applications that would seem unimaginable, let alone impossible. And so I feel that making connections has sort of helped us in not only defining possible, but redefining possible. And I think that completes the whole link to the theme. And to conclude my talk, I'd like to talk about this anecdote from Michael Faraday when he was working on such experiments. He was asked by someone, Michael Faraday, of what use is this work that you're doing? And if you're any one of us, any scientist, we go crazy. We go, are you mad? This is amazing stuff. I mean, for us, if we find something like this, it's mind-boggling. But what he replied was simply amazing. What he said was that, sir, of what use is a newborn baby? Now, I don't know about you guys, but I've got 3 little siblings, and I've seen all of them grow. And I can assure you, newborn babies aren't of much use. But what newborn babies can have, is potential. And what they can do is grow into, probably become the next Michael Faraday, or even Einstein, I don't know. But it's that potential, and it's the same way an idea and that connection can have potential to grow into something that could potentially change the way we define possible. And if that is a brilliant way of example of defining possible, I don't know what is. Thank you very much.